Welcome to Maths with Bob. Today we're looking at the second in a series of integrations by substitution. We're having a look today particularly at something called the t-results or the t-substitution. Now what is the t-substitution? Well, the t-substitution is that we're going to substitute t is equal to tan, normally x on 2, usually we write like this. Okay, so this is the substitution we're going to use, and we're going to use this in particular cases, usually when there's a sine or a cosine by itself, usually. But the first thing we need to do is we need to differentiate it, and we need to go dt dx, you can see here, is equal to what? A half sec squared x on 2. We need to rewrite sec squared as 1 plus tan squared. Okay, 1 plus tan squared x on 2. Okay, basically, and rearrange this expression here. Basically, try and find an expression for dx in terms of dt. So we multiply it by 2. 1 plus tan squared is 1 plus t squared, you can see here. So this is really what, a half of 1 plus t squared. Okay, that's dt dx, I should say. And then multiplying it by 2, we end up getting what? 2 dt all over 1 plus t squared is equal to dx. So that's the first thing. Okay, so we end up getting a result to replace the dx with, which is a 2 dt over 1 plus t squared. Now, there are a couple of other things we're going to need, and that is basically expressions for sine x, cos x. Okay, so we need to actually look at what's called our half angle results, or if you like, you look at the double angle results and then halve the values. But the idea is that I always think it's just as easy to just create the triangle. Okay, this is the x on 2, and you know its tan is t, so it's opposite over the adjacent, which is 1. Then the other side obviously is the square root of 1 plus t squared from Pythagoras, and then we can work out what what is sine of x on 2. You can see here sine of x on 2 is just the opposite, which is t over the square root of 1 plus t squared, and you can see the cosine of x on 2 is just equal to 1 over the square root of 1 plus t squared. And now what you do is you actually use your sine or your double angle results, and then you just halve them to get the x. Well, let's actually do one. Okay, what do we? Okay, let's look at. We know that sine 2x is equal to what? 2 sine x cos x. Okay, this is a double angle result. Let's halve the angles now. So we get sine of x is equal to what? 2 sine x on 2 cos x on 2. And then we just substitute in these values, which we've already got. Okay, that's going to be what? 2 sine, which is just t over the square root of 1 plus t squared, times the cosine, which is just 1 over the square root of 1 plus t squared. You can just see here that's just equal to 2t. Okay, just going to equal just 2t over 1 plus t squared. Okay, so that's what sine x is. Okay. Now notice before we actually had sine x on 2. So this is the expression we're going to substitute in for sine x in the integrals. Okay, let's have a look at the cos one. Okay, so let's have a look at the cos one. Okay, you might remember that the cosine is the cosine of 2x is cos squared x minus sine squared x. So let's just write that down. Okay, what was the cos of 2x was equal to what? Cos squared x minus sine squared x. We can rearrange these to get the substitutions for the sine squared and cos squared in the trig integrals as well. But let's put it in. Okay, so we just halve the angles now. We know that the cos of x is equal to the cos squared of x on 2 minus the sine squared x on 2, and we just need to square those two above results and subtract them, which I'll just do quickly. What's cos squared is going to be 1, so it's just going to be 1 minus t squared on 1 plus t squared. And this is the expression we're going to substitute in for the cosine of x in terms of t. Okay, so let's actually have a look. Well, rather than derive the t results every single time, everyone normally remembers this triangle. You can see here we have the, let's have a look. We have the 2t, okay, opposite the x, okay, coming up this way. Okay, and we have the bigger side, 1 plus t squared over here. Okay, you might remember we derived some of these from the half-angle results before, and the 1 minus t squared here. Okay, so once we've actually got this triangle, we can now just straight away write down the substitutions for sine x. So we can see here what sine x, just pretty much easily opposite on the hypotenuse. You can see the cos x, you can see here, we derived before 1 minus t squared on 1 plus t squared. So just be t, 1 plus t squared, and then while we're here, the tan x substitution is going to be what? 2t on 1 minus t squared. Okay, alright, so this is actually, remember, this is t is equal to tan x on 2. Okay, alright, okay, let's move on to another example. Okay, well, let's have a look at example 1. Here we have a dx on a 2 plus 3 cos x. Now, normally we're going to use the t results when we have something like, a cos x or a sin x floating around by itself. And you'll see we're going to go through a few examples. Now, with the dx, you might remember, we actually just put in 2 dt on a 1 plus a t squared, okay? So we're just going to transform this integral, if you like, via the substitution. 2, okay, I'll write that as 2 1 plus t squared, basically because we're going to have a 3. Now, a cos, you might remember, was actually 1 minus t squared on 1 plus t squared. So I'm going to put it all over 1 plus t squared. Okay, this is the first thing we do. We normally would then cancel. You can see here, we can cancel here, and we sort of try and put this together a little bit and see what we can get. Okay, so we've got 3 and 2 is 5, 2t squared minus 3 squared. So it's going to be basically equaling, okay, what? The integral of, okay, the 2 is still going to be there, 2 dt. The bottom is now going to give us, 5 minus t squared. Okay, now, this is going to, require a bit of partial fraction work, so we're going to need to write this as something, let's have a look. So we're going to need to write it as something, well, break it up, 5, actually, root 5 plus t, so we need to have a and we need to have a b over a root 5 minus t. Okay, so this, you can see this is partial fraction breakdown. And we're going to be using these sorts of integrals a fair bit because they're going to turn into logs, and we run across them quite a lot in the t substitutions. Okay, so let's actually have a look at how would we do this sort of integral. Now there's obviously going to be a 2 which we're going to have to equate to. So how will we do this? Well, we normally say, okay, we need to go 2 on 5 minus t squared is equal to what? A on, okay, remember this is the difference of 2 squares, so it's going to be root 5 plus t plus b over the square root of 5 minus t. Okay, so we're going to need to find the a and the b, and what we normally do is we go, therefore, okay, let's do it, therefore, okay, what 2 is equal to a lots of, now, we multiply everything by 5 minus t squared, so we're going to get a root 5 minus a t here, plus a b lot of, now we multiply that by 5 minus t squared, and we get a, what, a root 5 plus a t here. Now, obviously we're going to select some really nice values to find out the a and the b, so let's have a look. What values would we select? Okay, so let's select, I'll just write it up here, if a is equal to, what, root 5? Okay, I shouldn't say a, I should say t. Okay, so that's actually, okay, well we're going to need to make a bit more room, so I'll just rub out a few things and rearrange this slightly. So hold on. Okay, I've just rewritten this, rubbed out a few things. We need to now select actually a value for t, which, I mean, this is true. This is true for all values of t. So we can actually select some really nice values of t. Let's try, let's let t equal, say, root 5. Now, if t is equal to root 5, you can see here the a would drop out completely, and I'll get, oh no, hold on, we've got a problem here. There's actually one of these signs should be a positive. Okay, so Okay, you can see here I just rubbed out a few things and rewritten this partial fraction problem. Now we have a 2 is equal to a lots of root 5 minus t plus a b lots of root 5 plus t. Now we know this is actually true for all values of t, so we're just going to select some nice values of t actually to make life a bit easier for ourselves. So if we let, say, t equals, say, root 5. Now if t is equal to root 5, you can see here that that drops the a out, and we'll end up getting that 2 is equal to b times root 5 plus root 5, which is just 2 root 5. And you can see here, okay, b, so b is equal to, okay, 1 over root 5. If you let t equal another nice value, minus root 5, you can see here that the b will drop out now, and then we'll end up getting what, therefore, okay, what, 2 is equal to minus root 5 minus root 5, so it's going to be 2 root 5 lots of a again. So a is going to be equal to, again, 1 on root 5. Okay, so we need to now put this into the integral, and we need to actually have a look at what this does. So we're going to say, okay, well, okay, this is going to, now this integral here is going to equal, okay, now you can see here I've used the 2 already, so I'm going to have a 1 on root 5. Let's put the 1 on root 5 at the front. Okay, I'm going to have a 2 fractions now. It's going to be okay, a 1 over root 5 minus t. Okay, plus a 1 on a root 5 plus a t. Okay, this is going to be a dt. And you can see here these are going to be logs. Okay, and you can see that I'm going to need to, okay, first up, what happens here? So I'm going to say, well, this one, the first one, will, okay, this one, okay, you'll see here I've got a minus t on the bottom, so I need to put a minus at the top, so that's going to create a negative log, so it'll go on the bottom. Okay, this one here would create I've got a positive t, so its derivative is 1, okay, so it's going to be so that would then give us what? 1 on root 5, okay, these are going to be ln's, so they're going to be ln, and the first one was a negative, so that should be on the bottom, okay, root 5 minus t, okay, we've got the invisible pen working. Okay, so let's go back, okay, so let's actually have a look at this section. Okay, so these let's have a quick look. Okay, so if we have a look at this part, you should be able to see, okay, I've got a negative t on the bottom, its derivative is negative 1, so I need to put a negative on the top and take a negative out, so that's going to create the negative log. If you have a look at the other one over here, this one here, I've got a 1 on root 5 plus t, its derivative is just 1, so that's going to be the positive log side. Okay, so this is going to give me what? Well, this will give me, if you like, 1 on root 5, there's going to be an ln now, there's, okay, the root 5 plus the t is on the top, and the root 5 minus the t, because that was a negative log, is on the bottom. Okay, so the log of that expression, plus a c. Okay, now you'll notice something. We now have got t's in our final result. We need to go back to the original variable. So we need to put tan x on 2 actually for here. So the final step is, after you've done all this, you go back, revert to the original variable. These are indefinite integrals, I should say. We have the constant here. So ln, so it's going to be root 5 plus, okay, tan x on 2, which was the t, and then the root 5 minus the tan x on 2. That's all, obviously, the log of all this whole expression, plus the c. Okay, so I'll just leave it there. Well, okay, here's example 2, dx over 3 plus 2 sine x. Okay, now you can see here we're going to let, this is a t result one, okay, there's a sine or a cosine floating around by itself in the numerator denominator, and we'll just let t equal, obviously, tan x on 2. Okay, we're going to just replace, we've derived the expression before that, 2 dt on 1 plus t squared is equal to dx. So let's actually just change this integral. Okay, so it's going to be, okay, first up, 2 dt on 1 plus t squared in the numerator. Okay, we're going to have a 3 now, and a plus a. Now I'm going to multiply that by 1 plus t squared in a minute. So I'm going to rewrite 3 as 3 times 1 plus t squared, or 1 plus t squared, plus 2. Now the sign, remember, the sign was actually just 2t. So it's times 2t on 1 plus t squared. Okay, so you can see there's a, oops, it doesn't look like a t over there. Okay, there's a t squared in the numerators, or I should say denominators of each of these fractions. We can cancel those, so we can actually simplify this to what? 2 dt over, now it's going to be on the bottom 3 plus 3t squared plus 4t. Okay, so we're now going to, you can see here we now have what's called a quadratic denominator, and we're going to now proceed with forming what's called a quadratic denominator. Okay, how are we going to do this integral? Well, I think I would normally take as many constants out as I can. So let's actually take the 2 out. No, I think I'd take out the 3 out from the t squared on the bottom and just see what happens. Okay, we've got a dt over here. Now we have, let's rewrite that as a t squared. We'd have a 4 on 3t. Okay, take a 3 out, so we have a 1 here. Now, okay, so this is actually a quadratic expression in the denominator, okay, and we need to complete the square. So the first thing we'd do is we say, okay, that's 2 on 3 integral, okay, dt, okay, over. Now, remember when you complete the square, you halve the coefficient, so it's going to be plus 2 on 3 squared. Now I need to subtract that off, so I'm going to have a plus of 1, but I'm going to also have a minus a 2 on 3 squared, okay. So that's obviously going to simplify to, let's have a look, 4 ninths, 1 minus 1, so it should be just 5 ninths. Okay, so let's actually just simplify that now while we're here. That should be just, okay, what? 5 ninths here. Okay, now hopefully we recognize this as a standard integral. This is the inverse tan integral, okay, which is basically, we now have to apply one of the standard integrals. Now, what standard integral is this one? Okay, let's actually write this down. Okay, this is the integral. I think it's the a on a squared plus x squared dx equals inverse tan x on a. Okay, this is the standard integral. Okay, so we're going to now apply this. Okay, let's apply this standard integral. Okay, you can see it's an inverse tan integral. So the first thing we'd probably do is just adjust it slightly. Okay, you can see here we need an a on the top. Now a, okay, if you have a quick look, this is actually a squared. Okay, so we know that a is the square root of that. Okay, so let's actually write, okay, the square root of 5 over 3 dt, okay, t plus 2 on 3 squared. And let's just write that as root 5 on 3 all squared. Now, rather than go through another substitution and let u equal t plus 2/3, we straight away know that in fact du is actually equal to dt. Okay, this is a linear expression, so we can actually straight away apply the standard integral. But there's one thing which, when I put that a in, I need to adjust the integral. Okay, so back to what it originally was. So I need to multiply the front by the reciprocal, 3 over root 5. Okay, and you can see here I would just cancel the 3's, and this would now give me just what? 2 over root 5. Now applying the standard integral now to it as the inverse. It's in standard form. Okay, so it should be just inverse tan. Okay, u, which would be the t plus 2 over 3, all over the a, which is actually root 5 over 3. Now I can simplify this slightly by multiplying the top and bottom by 3, and this should be equal to what? 2 on root 5 tan to the minus 1 of 3t plus 2 all over root 5. Okay, and then we'd back substitute for the t. Okay, what the original expression was, in fact, remember, t was equal to tan x on 2. So we go 2 on root 5, putting everything back into the original variables, inverse tan now becomes what? 3 tan x on 2 plus 2, all over the square root of 5. And don't forget the constant of integration. Okay. Well, there we have example 2. We'll try another one shortly. Okay, here we have example 3. We're going to just obviously straight away go into a bit of the substitutions. Let's do a dx, remember, was 2 dt on 1 plus t squared. Remember, we're doing the t substitutions here. So we now need, this is 4, lots of our sign. Remember, was actually 2t on 1 plus t squared, and cos was 1 minus t squared on 1 plus t squared. Okay. All right, so we can straight away divide everything by, or if you like, just cancel the 1 plus t squareds, if you like. Let's actually see what would that be. That would give us what? 2 dt on the top. Let's have a look. 2 4s are 8t plus 3 minus 3t squared. Okay, now here we have a quadratic in the denominator, and you can see here, if I can't factor that, I'd have to actually complete the squares. But luckily, we can factor this, and basically we're going to get its factors to nicely, actually. Integral 2 dt over, now the factors are 3 minus t, okay, and 1 plus 3t. 3 minus t, 1 plus 3t. Okay, now this becomes now a partial fraction problem, and let's actually just do the partial fractions. Okay, well, let's actually break it up into partial fractions. So we need this to be a over now 3 minus t, and notice these are linear expressions, so they're constants in the numerators. Okay, here 1 plus 3t. Okay. We can put brackets around it if you like. We don't really need those brackets. But now, if we now multiply by both sides of this equation, okay, by 3 minus t times 1 plus 3t, we end up getting that 2 is going to equal a, lots of what? 1 plus 3t. You see those other factors cancel, plus b, lots of, okay, 3 minus t. Okay, that's the first thing. And what we do now is we let t be some very nice values. So if you let t equal something which actually would drop out one of the a's or b's. So try 3 to start with. If we let t equal 3, we can see the b would drop out, and we get basically what? 2 would be equal to a times 3 3s are 9 and 1's 10. So 10a would equal 2. And a is equal to 1/5, okay? So basically, this value here is what? 1/5. Okay, if we let, okay, t equal now what? Okay, now what's going to drop out the a? Well, 1 plus 3t is equal to 0. Say t is equal to minus a third, okay? Minus 1/3 would drop the a out, and that would give us minus a third, minus a third, plus a third, and 3. So we get that 2 is equal to, what, 3 and 1/3 lots of b. Then we just rearrange that. That's 10 on 3, so it's 6 on 10, 3/5. So, okay, therefore b is actually equal to, okay, 3/5. Okay, so once we've got those values, we can now put them into the integral. So I'll just put them into the integral. Well, okay, you can see I've just put those the a and b values in, and you can see hopefully that they are going to be log integrals. We take a fifth out, okay, and let's first of all take 1/5 out. Becomes integral. You can see here just 1 on 3 minus t plus 3 over 1 plus 3t. And that's nice, because the derivative of 1 plus 3t is actually 3, so that's the log straight away. And the only problem is that the other one actually, we'll need to adjust it. So we need to do, I'll just show you what you need to do with this one. You just need to put a minus 1 in here and just make that the negative of that. And then you can straight away hopefully see that these now are logs. Okay, so they're both logs. One's positive and one's negative. So what would happen? Well, we end up getting 1/5. Now the positive log would be Okay, 1 plus 3t, and the negative log is 3 minus t. Okay. And then we'd substitute back for our t value, which was variable in terms of variable x, so it would be 1/5 of what? ln 1 plus 3 tan x on 2 all over 3 minus tan x on 2. And not forgetting our constant of integration here. So, okay, well, look, I'll leave it there for the time being, and thank you for watching.